Hi everyone, and in this video, we are going to uncover a really important paper in the field of artificial intelligence, deep reinforcement learning, or in the field of geopolitics these days. No kidding. The thing is, this paper has brought a lot of revolution in this complete world because of its open source nature and how it beats other closed source models. And we are going to look into what the challenges were and how these people are overcoming them. And the paper I am talking about is not exactly DeepSeek R1 because I went through the R1 paper as well, but not a lot of details about training and stuff are given there. But what I found interesting is the reasoning. Reasoning is very important for an open language model and for any language model, to be honest. Reasoning is something that is very, very challenging. And I wanted to understand what kind of model and what kind of technique could help the model learn this reasoning better as compared to human, or even if we just compare different models, which particular method works the best for which model. So today we are going to uncover DeepSeekMath, pushing the limits of mathematical reasoning in open language models. Well, mathematical reasoning is a significant challenge for language models. Current cutting edge models like ChatGPT 4, Gemini Ultra are not publicly available, and open source models lag in this performance of mathematical reasoning, especially. DeepSeek Math is particularly a domain specific language model focused on mathematics. So, in this video, we are only going to talk about mathematics as such. In the next video, probably I'll go through the R1 as well, but this video is important to understand the coming video because in this video I'll talk in detail about what kind of corpus they're using, the data set, how they're training, and we'll dive deeper into some proposed new reinforcement learning method called GRPO. I'll be talking about that in quite detail in this video. So this is going to be very important, very fundamental, and if you're a developer, if you want to develop your own model sometime, DeepSeek Math and DeepSeek in general is an organization that provides really small models which compete models that are 10 times or 100 times larger than them. So that's why this video is important. It significantly outperforms other open source models, approaching the performance of GPT-4. The key success of this paper is that it provides a large scale, high quality pre-training corpus and a novel reinforcement learning method called GRPO, which I'll be talking about in really, really good depth in this one. So let's get to the paper now. So, as I told you, in this video, we are going to focus more on DeepSeek Math rather than the DeepSeek R1. And the reason is simple. We want to understand what kind of data set that they are using, which is, in my opinion, is pretty brilliant, as well as a little genius thing to do here is an introduction of GRPO, that is Relative Policy Optimization, and it's just a variation of proximal policy optimization, which I know we have not covered in this playlist yet, but we'll be covering that very soon as well. I'll try to simplify entire GRPO as well, so don't worry about that. Fine, so let's go through this line by line in this paper. They are actually introducing DeepSeek Math B 7B, 7 billion parameters only, which is pretty small. And key thing about it is that it scores 51.7% on competition level math benchmark, which is, I think it's American or English mathematics benchmark, which is pretty standard. It outperforms every single open source model. It performs at the level of Gemini Ultra and GPT-4, which is really huge because this is an open source model and it's very, very small as compared to Gemini Ultra or GPT-4, who might be an hundreds of billions of parameters, or probably trillions of few people say, but not the point. It Even if like if model is like 10 times bigger than its this model, then also it can either outperform it or match its performance. That's a really huge deal, right? Okay, so what they're doing is they are harnessing the potential of publicly available web data, and there is a really good, and it's not an exaggeration that they are using meticulously engineered data selection pipeline. No, they are not exaggerating, it's actually true. We'll get into that detail as well, that how exactly that pipeline is working, and I feel that it's pretty genius as well. And second thing that they're introducing is amazing. It's called Group Relative Policy Optimization. I'll call it GRPO from now onwards. It's basically a variant of Proximal Policy Optimization, PPO, which is a very popular deep reinforcement learning method. Well, this enhances the mathematical reasoning abilities while concurrently optimizing memory usage of PPO. So the only issue is that even if they started with PPO, PPO was consuming a lot of memory because there were two different models which needed to be trained simultaneously in order to improve one of them. Well, we'll get into those details, that how they are reducing the memory usage of GRPO as compared to PPO. What are the changes that they are making throughout this video? The few things that I'm going to focus more on are how the data set is generated, how they're doing reinforcement learning, of course, the chain of thought that they are introducing in this paper. And okay, a chain of thought is pretty old, but the way that they are doing in this paper is what I meant. And lastly, probably model distillation. I think there are a lot of videos about model distillation, but I feel that in this paper, I want to discuss more on the data set that they are using, how they're accumulating that, and how they are planning to train their policies that are from the GRPO, and how it is bringing such a huge impact to the entire deep reinforcement learning ecosystem as well as the AI ecosystem in general. So let's get through. Uh, well, yeah. So it has significantly outperforms the mathematical capabilities of open source models. We have already seen that. So DeepSeek Math Corpus is what they are introducing in this paper. It's a large scale, high quality pre-training corpus comprising 120 billion math tokens. Well, one term that disturbs me here is what is high quality. I feel that it's not high quality. It's what they really mean is uh, more relevant data set instead of high quality. What is high quality? For me, this water is high quality and this water is low quality, or for some people, this water may be high quality and this could be low quality. It just it's a very very subjective thing, and I don't think that high or low quality are something that we can judge. But what do they probably mean is it's a more domain specific or more relevant data set for good capability in reasoning, right? So reasoning is what we are going to focus most of in this video, and it is extracted from a common crawl CC using a fast text based classifier, which we'll be looking into soon. So they have employed the classifier to mine additional positive instances from common crawl, which are further refined through human annotation. Human annotation is very difficult to do, so probably that's not the case. That's my own hypothesis, but let's look into it. The classifier is then updated with the enhanced dataset to improve its performance. So, what they mean by human annotation is it could be another human level large language model. It could be a human which is annotating small part of it, and there could be a model that could just use generative AI to build similar data set or a similar refining of the data set, something like that. Because it's my own hypothesis and it may not be true, but you can believe in whatever you feel good, whatever you feel good about. The reason for my belief is that if they are using a common crawl data set, and it's really, really massive. And we have already seen that they are collecting 120 billion MAT tokens, which is impossible for a human annotator to do, or even a huge team of human annotators could do. Fine. So let's not get into those controversies, but we'll try to uncover that as well. Well, so let's talk about the contributions of the paper. The key two contributions of this paper are math pre-training at scale, a huge scale of billions of tokens, and exploration and analysis of RL. So let's go through one by them. Let's go through them one by one. So as I said, designed data selection pipeline. They have given a really good diagram and explanation of that in this paper. I'll show you that soon. But what I'm looking for is they're trying to answer the long-standing question that does knowing to code help you in your mathematical reasoning or not? Well, it's a long-standing question because you see a lot of parents try to teach their children how to code, and they think that okay, this might help them in mathematics, or some people even think that okay, teaching mathematics to my children or students or anyone could help them learn coding faster. So are coding and mathematics related to each other? As humans, or as programmers, we might think that okay, yes, it could be possible that understanding code might help us in mathematics, or knowing or loving to do mathematics a long time could help us in our coding skills. So is this really true or not? That's what they are trying to figure out in this paper, and the insights are quite counterintuitive, or the insights are partially what we think and partially something new, which I'll be talking about soon. So yes, what I love about this paper is GRPO. It's a new reinforcement learning technique, and so GRPO foregoes the critical model, instead estimating the baseline from group scores. What I mean by that, I'll show you in the code soon. But what it does is it significantly reduces training resources compared to PPO, and significant means more than 50% probably. So what it does is it enhances the performance of your instruction tuned model DeepSeekMath instruct by solely using instruction tuning data. And we observe that enhancements in out of the domain performance, which is not something that we can think of. That when we talk about reinforcement learning, we think that if an agent is doing good in this environment, if we give it a completely new environment, will it be able to perform well or not? Turns out that GRPO approach is actually enhancing, and it's actually enhancing the performance also in out of the domain questions and answering them very well. So that's something that we should have our eyes on. So for evaluation of the model, they are using Chinese and English mathematical reasoning benchmarks. So they have listed a lot of benchmarks. They talk about math benchmark a lot throughout this paper, and I think SAT is fine. SAT is not really mentioned repetitively, but math is really mentioned repetitively a lot of times, and I think GSM 8K is also mentioned quite a lot of times. So they talk about English and mathematical reasoning. They talk about formal mathematics, that if we give it some formal mathematical questions, is it able to answer them or not? And later on, a very important thing is that natural language understanding. We are going to look into these things in little bit more detail very soon. But let's start talking about the data set that they are creating. So they're constructing a DeepSeek math corpus from Common Crawl, and they are presenting uh, an iterative pipeline that demonstrates how to systematically gather a large scale mathematical corpus from Common Crawl. What they're doing basically is they have first they choose open web math, a collection of high quality. Again, high quality here means just more mathematical related or more mathematical relevant as their seed corpus. That's where they begin their entire journey of collection of data set from. So that's already huge. And just because it's high quality does not mean it's perfect. There could be a lot of problematic tokens as well. So they train a fast text model, and it's linked here, fasttext.cc. And to recall to recall more open web math like mathematical web pages. So it just collects a lot of web pages which are similar to open web math. So then they randomly select 500,000 data points from the seed corpus, that is this open web math, as positive training examples, and another 500,000 web pages from common crawl as negative ones. So there's the beauty of reinforcement learning. You don't only learn from the good examples, you also learn from the bad examples. So I think that's where reinforcement learning can come into picture and could help a lot of different discoveries in the future as well. So they're employing an open source library for training. Yeah, again, so this is that one. Fast text model, fasttext.cc is another open source library for configuring the vector dimensions, everything like that. And this is the pipeline that they are talking about. First, there is this math seed. Forgot the name. Yeah, open web math dataset. They train a fast text model out of it and recall math related web pages from common crawl and deduplicate the common crawl 40 billion HTML pages, which is quite a lot. Discover math related domains, and they annotate math related URL paths from labelers, then they do deduplicate it again and again just to make sure that they're not repeating anything, or there is so basically deduplication is a process where they're trying to minimize the amount of bias on the data and trying to bring more variation into the data, which is going to help them a lot. Honestly, they have spent a lot of time and a lot of thinking about how they are going to collect data, and in my opinion this is one of the biggest reasons why it is performing so well, and is making very less mistakes while in inference as well. So to reduce the size of original common crawl, that is this really huge. Okay, they have. I think it's here. So there's this huge common crawl data set. They have employed URL based deduplication and near deduplication techniques, resulting in 40 billion HTML pages, which are just fine, right? Which are just okay. And mathematical web pages from deduplicated from yeah. So okay, another good deal about this paper is that they are filtering out low quality mathematical content by not just using a threshold that okay we'll just cut down at some point. They're actually ranking all of these web pages on some metrics, and then they are preserving only the top ranking ones. They are leaving everything else. It's not like they are doing 50-50, or they are actually just removing the bottom ones. No, they're actually only preserving the top ranking ones. Fine. So in the first iteration they choose the 40 billion tokens, and then they keep on increasing the number of tokens and the data set as well. So there's a good amount of explanation on how this process is taking place, and this is something that we should talk about. We noticed that nearly 98% of the data in the fourth iteration, by the way. So I was talking about the first iteration only. Similarly, they keep on doing the same process, and they noticed that nearly 98% of the data has already been collected in the third iteration, so they decide to cease data collection. So they this is how they are collecting the data, and in the fourth iteration they believe that 98% is already there in that data set, so they just stop it right there, stop the data collection there. Right, so this is how they are avoiding benchmark contamination. You can read through it, it's not very complicated. So the best thing about this paper is that it is very well written and very beginner friendly as well. Even if you have no knowledge about uh, deep reinforcement learning as an expert, even if you have just the basics of reinforcement learning with you in your head, you are good to go. Just read through this paper. It's going to be fine. Uh, yeah, I think evaluation results due to their high quality work. So they have created a higher quality corpus dataset which covers multilingual mathematical content and is the largest in size. Wow. Okay, largest in size. I didn't read it earlier, but that's pretty cool. So first of all, it's high quality, and they are evaluating it in 8 mathematical benchmarks. Yes, this is important because benchmarks show us that which model is doing better and how good is it. What they're using is they're using few short chain of thought prompting, a very important technique that is introduced by this guy somewhere in 2022. And this is the table that we're going to look into. It's table number 1 of this paper, which will show us that how few short chain of thought prompting is helping us perform so well in all the 8 mathematical benchmarks. So should we just get right into that table, or wait, let me show you a few more things. High quality, it's multilingual. Yes, by the way, yes, it's multilingual and multiple languages featuring English. Yes. Dominantly featuring English and Chinese as one of the most represented languages, which is, I think, in my opinion, it's true. Mandarin and English are two of the most spoken languages. And it is also large scale. High quality, I think they have already mentioned largest in size, but let's read through large scale as well. Several times larger than existing mathematical corpora. Wow, that is pretty cool. Fine. Evaluation. Okay, yeah. So what they introduce is they introduce DeepSeekMath base 7B, 7 billion parameter, which is a base model with strong reasoning capabilities, and especially it's good in mathematics. So that's what they want to tell you about. And the model is initialized. So this base model was initialized from a DeepSeek coder base v1.5 version 1.5 and 7 billion parameters again, and trained for 500 billion tokens. Fine enough. Now, the distribution of the data is pretty cool. Is that they are not only using the DeepSeek Math corpus. The DeepSeek Math corpus, yes, it is a majority in this entire domain. Um, so it's like 56% of DeepSeek Math corpus. But at the same time, they're also using algebraic stack. They are using archive. They are using GitHub code, and they're also using 10% natural language data, which is astonishing that. And if you think about it, probably while reasoning something, that okay, if I've got 5 apples, if I give it, if I give two of them to someone else, if I throw one of them in the trash, how many do I have? So this is basically an English statement, and this is still a mathematical question, and it still uh, gives you the ability of reasoning, isn't it? So this makes sense that having a 10% of natural language data is important, even if you want to go with mathematics prone or very much a mathematical expert, right? And again, 20% is GitHub code is still a hypothesis that they're holding that okay, this might be helpful, this might make the performance worse. We don't know about that. We'll look into it soon. Okay, so how the assessment is taking place. And without relying on external tools, solve mathematical problems using tools and conduct formal theorem proving. These are the three things that they want to show their prominence in. That okay, without using any IDE on the web, or without using any compiler within their system, they want to be able to solve mathematical questions. So okay, if we have those tools, can we solve these problems better? And also conduct full formal theorem proving. So while okay, let's see here. 10% of archive, right? I forgot to mention this. But archive is basically a huge collection of technical papers, technical, non-technical. I think there are a lot of different archives. So with technical papers, they have got really good research paper in mathematics and science and everywhere. So it's very obvious that they will have a lot of different equations with them. But the problem with these papers is that they do not really carry complete derivations of proofs or anything, right? If you are an author, you won't be proving everything step by step. You'll just skip a few steps in between and just assume that your readers will be able to understand them, right? So according to me, and I think this is what they come up with the conclusion at the end as well, that training only on archive is not a good idea, but probably somewhat it will still help you in some or the other manner. It won't harm you a lot, basically. That's what they mean. But yeah, it's just basically depends on your use case as well. So can we conduct formal theorem proving or not? So that's what their question is about. Right. Also, so mathematical problem proving with step-by-step reasoning is something that is very important to them, and they are using few short chain of thought prompting as I discussed earlier, and these are all the benchmarks. Yeah, this is the table that is a little important because this shows that, oh, where is the huge table? Mm, I'm searching for table number one. Did I drop it somewhere? Or just a second. Mm, come on. Oh yeah, this is the paper that is important. These are all the math corpus that they're using. And this is the size of the corpus. Of course, this is the biggest one. And using a baseline, I think it's just simple DeepSeek LLM 1.3 billion. They're just testing if their math corpus is really working or not, if it is just good enough to train a huge model on or not. So this is just evaluating how good their corpus is. Well, it is just best out of everyone else that existed at this time. So yes, check mark that. Okay, we have a really great mathematical data set. Awesome. We have not really gone into reasoning just yet, but mathematics and reasoning are very much correlated with each other. So yeah, so what they do now is they test their model as compared to other models which are I think probably not mathematics. Yeah, okay. Yeah, so they're testing comparing this DeepSeek Math Base 7B with strong models on English and Chinese mathematical benchmarks. Yes. All of them are evaluated in chain of thoughts prompting, which is important again. So you will see this COT being used again and again throughout this paper, and that is one of the magical things about that makes reasoning possible, right? Okay, so of course, DeepSeek Math base is outperforming every single model on all of these benchmarks, and SET is one of them. Then CMath is Chinese mathematical benchmark. I think math is English mathematical benchmark. Yes, and it is outperforming. Perfect. So our base model is outperforming every single other open source model, a strong open source models and a strong closed source models. You cannot see OpenAI here yet, but you will see that later. You'll see that a few of them are really huge in nature, like 34 billion, and even if like Minerva, I'm not sure if I'm pronouncing that right or not. Minerva is also like 540 billion parameter size model, right? So we are still like DeepSeek Math is still in like 7 billion parameter model, which is pretty cool. Okay, a Minerva 540 billion model is closed source based model 77 times larger, which is which builds on Palm. Palm is I think by Google. Fine. So mathematical problem solving with tool use. So over here we are talking about mathematical problem solving with step-by-step reasoning. Here I don't think they have used any tools, but with tools as well, DeepSeek Math base is actually outperforming everyone. Yeah, it is. It is outperforming everyone, right? So models are prompted to solve each problem by writing a Python program where libraries such as Math and SymPy can be utilized for intricate uh, computations, which is pretty fine, right? So over here as well, we say that it beats Code Llama, it beats Mistral, it beats Llama, and pretty good. I think it's only about open source models right now, which is good enough, right? We have established the fact that okay, DeepSeek Math base is doing good so far. Now, on formal mathematics, which means that formal proof automation is beneficial to ensure the accuracy and reliability of mathematical proofs and enhance efficiency, which is important, but it's not really beating every single model here yet. So, they are using DeepSeek Coder, DeepSeek Math Base, and different DeepSeek models and comparing it with Mistral. It's not performing the best and it's a little far off from Mistral. So we can say that okay, math base is still not there yet, but we have not lost our hopes yet. And similar with natural language understanding as well of mathematics. So significantly outperforms the general model. Again, so over here Mistral 7 is a general model instead of a mathematical specific model. So that's important to note. Right. So DeepSeek Math Base 7B is outperforming Mistral 7B. That's it. Fine. So now we come into supervised fine tuning. Over here, they conduct mathematical instruction tuning dataset covering English and Chinese problems from different mathematical fields and varying complexity levels. So the problems are paired with some sort of chain of thought, program of thought, and tool integrated reasoning formats. And the total number of training examples is 776,000, which is pretty fine, good enough. And once that once they have done the SFT, supervised fine tuning, they use training, how the training and evaluation is taking place. Pretty decent stuff, but I don't think it's very new as of now. SFT is done by a lot of models, and I think it's not novel for this one, and could be performed well. Now, something important that I want to share here is on the competition level math dataset, our model surpasses all open source models. Fine. And majority of the pre-priority models. Yes, it performs much better than open source, but this time they are even competing with the closed source models. We do not know how big those models are, yet they are able to do it. But there are some caveats that they are underperforming as compared to GPT-4 and Gemini Ultra. Still, their performance is at some level comparative to them. Fine. Okay, here's the table that I want to show you. It's really significant here because DeepSeek Math Instruct and DeepSeek Math RL, both of them are important models, and you will see that how RL enhances the performance of Instruct. So whatever Instruct is to perform in, RL makes that huge leap that from 83% it goes to 88%. Huge performance boosts. And when RL was not introduced, it was just using Math Instruct. It was basically comparatively okayish and fine enough as compared to other open source models, which is not too impressive. But after implementation of RL, they could see this huge significant leap, which of course outperformed every single open source model, but also outperformed many, all of these models, all of these models as well. in mathematics. Of course, it could not really beat GPT-4 and Gemini Ultra, but that's fine. We do not know how big they are. They could be like billions or even a couple of trillion parameter huge. And over here, you'll see that Qwen is like 72 billion. MetaMath is 70 million, a billion, and Wizard Math is like 70 billion. It's like 10 times. These models are literally 10 times bigger than DeepSeekMath RL or DeepSeekMath Instruct. Yet, DeepSeekMath is outperforming them. This shows that, or probably does not really show that. Honestly, in deep learning, the number of parameters that you increase, the performance should increase. In general case scenario, if you see something contrary like this one, it is typically genius. It's really good thing to see, right? Fine. Over here we come with comparison between PPO and GRPO. Let's talk about PPO a little bit. So PPO is an actor-critic reinforcement learning algorithm that is widely used in RL fine-tuning stage of LLMs. And this is what the scary equation is. Over here, the pi theta old is the old policy model, and pi theta is the current model. Fine, makes sense. Q and O are questions and outputs sampled from question dataset and the old policy. So old policy will give you some output on this question. So that's what this Q and O are respectively. Epsilon is a clipping related hyperparameter. Clipping is introduced, I think, before PPO or was introduced in PPO. I cannot really recall exactly, but clipping is a method where we restrict the range of our output to some extent. It should not go below something, it should not go above something, and it looks similar to SVM, but in a different general scenario. I cannot really explain what clipping is exactly right now, so I won't comment on that much, but it's very popular knowledge. Okay, something important is that 80 is the advantage, which is computed by applying generalized advantage estimation. So PPO uses GAE based estimation, and it's based on the rewards RT and a learned value function that is VSI. Let's call it VSI for now. Fine. Um, the problem with PPO is that in PPO, a value function needs to be trained alongside the policy model. So you see there are these two trainable parameters, policy, the original policy model and the value model. These two need to be trained because the value model becomes the baseline to train policy model, which is little computationally expensive. I mean, like not little, but it's extremely computationally expensive because to migrate over optimization of reward model, the standard approach is to add per token KL divergence penalty from a reference model in the reward function at each token. So you can add this. Fine. So this was a problem with PPO. I think there are two problems. Yeah, fine. It brings a substantial memory and computational burden. So we are dropping PPO. How can we use something better? What can we do differently? So that's where GRPO comes into picture. What GRPO does is it obviates the need for additional value function approximation. So over here, you don't need this value function. So your learnable parameters become half, which is very good, right? Your memory becomes really less. Your computation becomes like twice easier as compared to PPO. And instead of using that mm, value function approximation model, it uses something else. What it uses the average reward of multiple sampled outputs produced in the response of the same question as the baseline. Let's read that again. Uses the average reward of multiple sampled outputs. So let's talk about this. So there are this question, that there is this question, there's this policy, and you give this policy this question again and again and again, and it generates multiple outputs. Let's say it generates g number of outputs, right? And with g number of outputs come g number of rewards, r1, r2, rg, right? And then we do some sort of group computation, and we send them to this another container called A1, A2, A2, A3. It's the advantage basically. There are different advantages that we get from every single reward, and then we use that to train our policy model. The hero of this entire mathematics is the policy model. Policy model is what we care about the most right now. Policy is what is going to give us the output. It's the agent that is learning, right? So for each question queue, GRPO samples group of outputs O1, O2, O3 till OG from the old policy pi theta old, and then optimizes the policy model by maximizing the following objective. This is the objective function. It's similar to what you see here in PPO, but there are subtle differences that you should look into. Over here, they're using KL divergence, and over here they are not using it. They are introducing that in place of value model. So that's the difference. Epsilon and beta are hyperparameters which you can set. Beta is still the coefficient of KL divergence penalty, which is here. Of course, we can see that. And epsilon is again the clipping hyperparameter. Uh, A cap, A hat IT is the advantage calculated based on relative rewards of the outputs inside each group. Fine. So inside each group only, which will be detailed in the following subsequent uh, arguments that they're making. But for now, it's okay to know that what they're eradicating this entire value model. Fine. Another thing that you should note is that instead of adding KL penalty in the reward, GRPO regularizes by directly adding the KL divergence between the train policy and the reference policy of the loss, avoiding complicating the calculation of advantage. Well, I think that this is not very difficult. It's not very much new if you have already known PPO earlier, but there are these small subtle differences which which bring a huge computational efficiency and training efficiency with it. So this is something that you should consider reviewing once. By the way, the whole process of GRPO training is mentioned here. I just explained that to you. So if you think that it's still unclear to you, I highly encourage you to go through this part once, and you'll get a much better idea. And it's kind of simple. It's not very complicated to read and understand. So highly encourage you to go through this. Okay, so iterative RL with GRP, I'm not covering it. It's kind of simple and very straightforward. Something that I find interesting is training and evaluation of DeepSeek Math RL, because now we want to evaluate it. We have trained it on RL as well. So how can we evaluate it? Based on the DeepSeek Math instruct, so it's basically based on DeepSeek Math instruct 7 billion. So it becomes the base, and DeepSeek Math RL is basically built on top of it. The training data for RL are chain of thought format questions. So every time we ask a question, we ask it to think step by step and then perform something. So that's important. And there are around 144,000 questions, which is really interesting. Mm, I think I somewhere saw a really good example of chain of thought. I cannot really find it right now, but I'll get into it later. Fine, so this is something important, and yeah, so they're excluding supervised fine-tuning questions, and we train our initial reward model based on the DeepSeek math base 7 billion. Fine. There are several hyperparameters that they talk about here. What is the learning rate for this model, and what's the learning rate for policy, KL coefficient, and everything. So if you want to reproduce this paper, it's kind of doable, not feasible, but they are giving almost all the information that you need to reproduce it. So kudos to the team of DeepSeek. Okay, finally, let's get into the discussions. This is very important, and probably the fun part of this paper entirely. What they are doing is code training benefits in mathematical reasoning. Remember the question that I asked in the beginning of this paper itself? That does code training help in mathematical reasoning or not? Pause this video for a second and think. Will we be able to code without learning mathematics? Or will you be good at mathematics without learning to code? Well, what do you think? Like it's a very simple question, right? Mm, According to me, both are interconnected, but they're not interdependent. My coding skills are not dependent on my mathematical skills and my mathematical reasoning ability. Like I've been doing mathematics since I was probably 3 or 4. Like, come on, I'm Indian. So, we learn mathematics at a really early stage, and I'm not even exaggerating. You can go and ask my mom and dad. But the thing is, at that time, I did not know how to code. I learned to code very much later in my life, like when I was probably my dad bought a computer and I learned it at 6 or 7. So after a lot of years, I started learning to code on some really basic programming language, not fancy at all. I started learning C after a long time, so I can't really recall. But the thing is, the entire concept is both of those skills, both of those things are independent to me. But I still cannot answer the question that is my coding ability good due to my early introduction to mathematics, or is learning how to code improving my math scores afterwards or not? I cannot really say because honestly, I've never seen it that way. But let's see what they find in this paper and more on to large language models rather than humans. Still, I think it's an interesting research that if anyone in psychology is thinking of. Right. So code training also improves mathematical reasoning without tool use. Fine. So this is where we get our answer. Another two-stage training settings. However, combining code tokens and math tokens for one stage training. So of course, wait, I skipped a few things. I skipped this part. I'm so sorry for that. They're they're doing some sort of two settings. First, they are using two-stage training, then they are using one-stage training. I want you to read through it. It's not complicated. You can just pause your video and then read through it for like 2 minutes. That's it. You don't have to understand it, just read it. Done. So after reading it, you will see that by combining code tokens and math tokens for one-stage training compromises mathematical reasoning without tool use. Make sense? So what they believe is that DeepSeek LLM 1.3 billion parameter, due to its limited scale, as it's a very small model, it lacks the capability to fully understand both code and mathematical data simultaneously. Right. So this is a very important assumption, and it's what that conclusion is. That just because it's a very small model, it has got very less number of trainable parameters. It could be possible that it is not able to fully understand the code and mathematical altogether. So fair enough. We totally understand. We find that okay, your DeepSeek LLM 1.3 is not doing good, so that's fine. Is there a couple of insights from reinforcement learning as well? Oh yeah. Oh, okay. This is also important. Archive papers seem inefficient in improving mathematical reasoning. That's what I told you earlier as well. That's not really very important to include or exclude archive papers, but it's probably because papers do not really contribute heavily in reasoning stuff. They just give you some hypothesis, they come to a conclusion, and that's it. They do not reason behind the conclusion, they do not reason behind why that hypothesis came into picture, unlike this video or unlike this paper, because over here they are reasoning, right? One of their conjecture is, it's not like they're even reasoning it, they're thinking of that, okay, could be a possible reason, right? So papers are really fuzzy in that nature, right? So again, what they're doing is, this conclusion has its limitation that should be taken with a grain of salt. So whatever I said, you should take it with a grain of salt. What they have not studied yet is this all things, that if you use only archive papers or not, if benefits of the archive paper would manifest themselves at a larger scale, larger amount of scale, or what I believe is like archive is not the best repository of finding best quality work. You will find great quality work on archive, of course, but that will be very sparse and you will have to search for it. You will find a lot of people just posting their papers or whatever documents they have into archive, and that might not be of great quality, because archive is open and anyone can put in any paper that they want. Quality could be a problem, quality could be some drawback. That's my own assumption. Fine. So I think they might have mentioned it, but I'm not sure. Fine. So then later on, there comes the insights of reinforcement learning. All right, so lastly, let's dive into the insights of reinforcement learning and what is this unified paradigm. So, what they're providing is a unified paradigm to analyze different training methods. So, there are different training methods called SFT, rejection, fine tuning, policy optimization, proximal policy optimization. I forgot what D stands for, distributed or something. And GRPO, we already saw that. So, and they are further conducting these experiments, and there are three components which are essential in this entire optimization, and basically understanding the differences between all of these three methods, multiple methods basically. So first thing is the data source D, which determines the training data that we are talking about. Next is the reward function by RF, which is the source of training reward signal. This is a very important term in deep reinforcement learning, so make sure you remember it. And lastly, we go through the algorithm A, which processes the training data and reward signal to gradient coefficient GC that determines the magnitude of the penalty or reinforcement or for the data. So this is what their own personal terminology is. If there comes a paper later on, they will give some different analogy to it, but this is what their baseline of what they want to do now is. So first of all, there is this SFT, supervised fine tuning. We have already talked about that, and human selected SFT data. That's fine. Now, secondly, they have given rejection sampling fine tuning and RFT. So there are two types of RFT and online RFT. RFT is basically offline and online RFT is online. A very basic difference, but it possesses very important or very significant jump as compared to, like, both are in comparison very significantly different in terms of accuracy. So you see, RFT is very low and online RFT is really high always. So initially they are similar, performing in a similar fashion, but at limit you will see that online RFT works better. What is online and offline? We'll talk about that soon. They have mentioned it, but it's a very common knowledge in reinforcement learning, so you should know it. Fine. So we summarize the components and that's fine. So this is what that table is. I think these are the components: data source, reward function, and this you should just change D with the data source, uh, by RF with the reward function, and gradient coefficient. Gradient coefficient over here, right here, should be replaced with different equations throughout this paper. So pretty simple stuff. They have kept it very modular so that you can use anything that you want in your own projects or anything. Fine. So observation about data source. What do they observe with that? So they have categorized this entire data source into two categories: online sampling and offline sampling. Online sampling means that training data is from exploration results of the real-time training policy model. So whenever we are running this policy, whatever observations we get from that, that is sampled as online sampling or online data. Whereas offline sampling denotes that the training dataset is from sampling results of the initial SFT model. So we already have that entire dataset. So it's not a surprise, in my opinion, that online RFT is significantly outperforming RFT on two different benchmarks. Not a new knowledge, but what we see is in the later stage, the data sampled from actor will exhibit more significant differences, and real-time data sampling will offer greater advantages. So this is what their conclusion is from the data source. Well, I'm not going through this entire section a lot in detail because the video is already too long. But if you want me to create it in a more deeper level, I'll cover this section in that manner. Well, another reason is that there are a few gaps in this particular paper, in this section itself, which I could not understand personally. I might need more time, but yeah, there are these gaps that do not really make sense as a reinforcement learning engineer here. But I'll definitely figure that out. Probably it's my mistake, or probably it's somewhere that they have hidden some or the other parts, which people often do, and that pisses me off a lot. But fine. Why RL works? This is important because our entire domain is deep reinforcement learning, and so they conduct reinforcement learning based on a subset of instruction tuning data, and it is significant performance enhancement upon the instruction tuning model. And let's look at the bold part. It seems that the improvement is attributed to boosting the correct responses from top K rather than the enhancement of fundamental capabilities. So this is something that I find very important. I'll highlight that. And there is some sort of misalignment problem in reasoning tasks using SFT model. That's also important because this means that SFT models are not perfect and RL models are performing better than SFT. That's what this paper is proving. Fine. I think I should highlight this paper as well. I will go through this after this paper. I think that this is of my interest. So, how to achieve more effective RL? This is a very important, and this is something that I want to know personally because whenever I develop an MDP of a problem or the equation of optimization for any given problem that my professor gives me or through the industry, whenever I get something like that, it becomes very difficult for me to effectively introduce RL into it because I have to take care of computation, I have to take care of how long will it take for me to train this model, and I'll also have to figure out what kind of reward function I'll have to use. These are all the different things that I have to give a lot of my time in. So knowing how to achieve more effective RL is definitely important if you want to get into the RL domain. So let's read this together. And I have intentionally left this blank. I have not really read it yet. I thought that I'll be reading with you all. So let's go through it. So within this paradigm, all methods are conceptualized as earlier. Okay, there exist three key components. Fine. So these are the three components that we should look into. This is what they are trying to tell us. And they're giving more information about these things in this part. And what they say is raw data of all training methods is the data source. Hmm, what is in context of RL? Refers to the data source of unlabeled questions. This is important because when we talk about RL is not only used for labeled data, it's very significant for unlabeled data as well. That's why RL is so popular and so widely used with outputs sampled from the policy model. So this is very interesting. And honestly, I've never worked with LLMs and RL, but after reading this paper, I am definitely inclined towards doing that. This is a potential reason for RL pipeline only improve this performance. Okay, in future we will explore. So that future discussion is that they want to explore in conjunction with advanced sampling, decoding strategies. Hmm, interesting. With efficient inheritance techniques. Okay, that's good. Um, so note that the techniques that they're using are not legacy. They are very new. So whatever papers that they have quoted, as far as I have remembered, all of them have been published or are referred from after 2020 or 2021, after that. So they are very latest. You will see that the papers from 2024, and this paper itself is from 2024, by the way. So just imagine how cutting edge their work is. Algorithms are important. I totally trust that. All methods now fully trust the signal of the reward function. Yes, it's important to design a reward function so that your model can trust it. We believe such weak to strong alignment methods will bring a fundamental change to the learning algorithms. Mm-hmm. Interesting. I'll come back to this soon. Reward functions. Mm, to enhance, we think there exist three important directions for reward models. Honestly, so reward functions are a few of those things which I personally lack in. I am very bad at designing reward functions and that wastes a lot of my time. So what usually happens is when you design a reward function, your model will start to learn in such a way just to maximize the reward, not to find the optimal path of doing it. So my professor, when I was learning reinforcement learning a couple of months ago, he he showed me a really good video. I cannot really recall, but there was this boat uh, circling circling an island where the boat was supposed to reach to the final goal destination. It was not supposed to circle the island at all. It was supposed to go to the final line, but why did it keep on circling the island without getting killed? Is because there were those small coins present around the island that if it collects, it gets those one, two, three, four kind of small rewards, and the agent was happy with that, right? Whereas it did not have any knowledge that going to the final outcome will bring it really huge reward or like 500, 600, or 1000 reward points. So designing a reward function is very essential, and the question is how to enhance the generalization ability of the reward model. This is important. This is what that boat lacked. It did not generalize on an entire environment. It just generalized around that island. That okay, as long as it is getting rewards, it is just doing well. It just thinks that. And we think about how to reflect the uncertainty of reward model. Yes, it's also true that it's not like whenever you do an action, you will always get the same reward. You will get higher reward, you will get lower reward. It's important to understand those differences as well. And how to efficiently build high quality process reward models that can provide fine-grained training signals. This is important as well. So in this paper, we went through the deep reinforcement learning deep reinforcement learning part in much more detail. And this is what this particular playlist and this session is all about. This video is all about, right? And my own inclination in robotics and reinforcement learning is in this direction itself. So I highly encourage you all to go through this paper and tell me what do you think about this, and how exactly is DeepSeek going to impact every one of us. Yes, I believe that it's not it's not really a really huge significant, like of course it's significant, but it's not really a huge deal. The kind of changes, the kind of propositions that they are bringing, I feel that they are quite common but never used in this domain, and that's why they are doing so well so far. But it's a contrary belief that this is not really state of the art. It's really these small practical tweaks that are really impressive, no doubt on that. But these are just small tweaks that there's no revolution that they are bringing to change everything. Yes, they are bringing GRPO, which revolutionizes or which brings small input towards deep reinforcement learning community, but everything else depends on the data and the quality of work that they're using, the algorithm that they have designed. And I definitely congratulate every single team member of DeepSeekMath. So that's it for this one. I'll see you in the next video next time soon. Take care.